review of chapter 14. And so, again, I want to focus on the idea of the directional derivatives and gradients, and then we'll take a look at some more problems that you might run into, like some optimization problems or Lagrange multiplier problems based on your homework. But just to review our directional derivatives and gradients, we have, I think I did this already. Do it again. We have a function. If you have a function going from R2 to R, then your domain is a two-dimensional domain. I don't know if you guys can see that. Your domain is a two-dimensional domain, R2, and therefore your gradient is two-dimensional. So that's one important aspect of the gradient. The gradient is as many dimensions as your input. Not your input and output, but your input only. So we can view this function z is equal to f of xy as a surface. But if we look at the gradient is only related to the domain, so that three-dimensional surface, the gradient on that three-dimensional surface will not make sense. But if we bring the gradient down to 2 dimensions, as in examine its level curves, then we can see that the gradient will be perpendicular to a level curve. On the other hand, if we have a function that can be expressed as a function of x, y, z equaling to a number, a scalar, then your gradient there is a three-dimensional vector. So now, if we take a look at a function, w is equal to f of x, y, z, and let w be a constant, now you have a surface, an x-y-z relation based on this equality, and that surface is called a level surface, and there the gradient is perpendicular to the level curve, level surface. Okay? So those are the perpendicular properties of the gradients. But one other important property of the gradient is that the gradient is a direction where you'll feel the fastest rate of change. So that depends on whether you're looking at a function in 3 dimensions or in 4 dimensions. It depends on the domain of your function. So if you have z is equal to f of xy, z is equal to f of xy, then the direction of fastest increase is a two-dimensional direction. If you have a function like you had on the quiz, where you have a w equals to something, a function of x, y, and z, then that's a three-dimensional direction, and that three-dimensional direction would lead you to the fastest increase. So one of the questions in your quiz was to figure out what the fastest increase in temperature is. All you needed to do is find a gradient evaluated at that point. So that's your three-dimensional direction. So I mentioned the gradients are perpendicular to a level curve, and so we've had a lot of discussion about tangent planes, because the vector perpendicular to the tangent plane would be perpendicular to a level curve. If I'll start with the case 2 in my notes here, and that is that if you have a function x, y, z equal to w, and you find a level curve or a level surface of that, then the three-dimensional gradient, partial with respect to x, comma, partial with respect to y, comma, partial with respect to z, that is going to be the direction, or that's going to be a vector that's perpendicular to a level surface. Okay? Now, if you have z is equal to f of x, y kind of surface, your normal vector, your perpendicular vector, is the gradient. But wait, the gradient only has two components. So if you want to look for a third component, it's going to be -1. Okay? So that -1 comes from this relationship, z is equal to f of x, y, between x and y. And if you bring the z over to the other side, you have f of x, y minus z equal to 0. And that looks exactly like a level curve that has an x, y, and z on one side. And if you take the derivative of that with respect to x, it'll just be fx. The derivative of minus z is 0 with respect to x. Derivative with respect to y is fy. And then the derivative with respect to z, this fxy has no z's in it. So the derivative of that is 0. And the z that you brought over is negative z. Now has a derivative of -1. Now you did not have that kind of a question on the quiz, but you probably will on the exam. Okay? All right, so the next page tells us properties of the directional derivative. This could be probably shortened to just one formula, but it's decided to take a look at it from a two-dimensional and three-dimensional point of view. But more importantly, we have the properties of the directional derivative, which kind of relate to the properties of the gradients as well. That the gradient is the direction of the fastest increase. Now that you know that the gradient is the direction of the fastest increase, when you actually want to find out what that rate of change is, what that slope is going to be given by the magnitude of the gradient. That's how fast it's changing. And then if you're going in the opposite direction of the gradient, since the magnitude is positive, and if you imagine you're on a hill, you go in the direction of the fastest increase, you're going to go upward. Well, if you go the opposite direction, you're going to go downward with the same slope. So negative of the magnitude of the gradient would be your slope going the opposite of the directional derivative, or the opposite of the gradient. Now, if you're moving along a level curve, if you're on the side of the mountain, you look at your map and you decide to follow the contour curve, then you're not going to change in height. So your directional derivative is going to be 0. So on the last problem on the quiz, when I said that this path that you would be taking happens to be on a level surface, then you're not going to change. That level surface is going to be the surface where the temperature is going to remain the same, whatever it is. Yeah?
If you actually did take the derivative and plugged it in, did chain rule, and dotted it and everything,
And got
would it
0?
ended up with 0, right?
Yes.
Okay.
If you would have done the other way, which is combine the path with the surface or with the function, and you would have had to do the chain rule or some form of the chain rule, then you would have gotten 0 anyways. So that also would be fine. Okay? All right. So I don't care if you download this or not, but it would really be good to have this as a reference if you don't have it already memorized. Of course, you can keep saying to yourself that the gradient is the direction of maximum increase, and the gradient is perpendicular to a level curve, and the normal is fx, fy, -1. So if you can remember all that, then that's great. If you can't, then maybe download this, copy it down, write it down a couple of times, and when next time you study, write it down, and then it'll stick a little bit better, I think. All right. So another big part of this chapter was the chain rule, which is a way you could have approached that last problem on the quiz as well, and also some of those homework assignments that you guys had, I think, had you guys try to describe the formula for the chain rule, and so that's going to be important. And then the last part is the optimization business. Okay. So having said all this stuff now, we have one of two things to do. We can either take a look at some of the review problems at the end of Chapter 14, or take a look at some homework problems that you guys are working on or will be working on. Any suggestions? Or we can go home, I suppose. Homework? Yeah. Renee, do you have one in particular already?
Yeah.
14.6 number. Oh, there's a lot. What? All right, directional derivative. Let's see if we could do this one.
Yeah, well, the thing is that my problem has two for the one, and even though I set out the practice version, I don't know if
I don't know. I don't know what to say about that. I could take a look at it after class and see. Should we skip this one then?
Yeah. We just did this.
Number 9? Oh, we can still do that. I think this will be quick. So, how do you feel about taking derivatives? Is that easy for you guys? Okay. So, the directional derivative is the gradient dotted with a unit vector. So, we need a couple of things. We need to make sure this is a unit vector, and then we have to find the gradient evaluated at 1, 1. So, this formula looks really simple, but it does involve a few more things. So let's first find u. So suppose I can try to figure it out and wait for your answers, but I'm just going to pull out Mathematica and calculate this stuff. So I'll say u equals 16, 48, and 24, and then I want to divide that. Oh, let's just make this equal to v for now. So it's v divided by. So the magnitude is the same thing as a dot product with a square root, right? So that's how I actually compute my magnitudes. So I get 1/7 and then 2/63 for my unit vector. So you find a magnitude, divide by that magnitude, and then plug it into here, and then this happens to reduce nicely according to Mathematica. The gradient of h is our next step, is to take the derivative of this with respect to r, s, and t. So if I take the derivative of this with respect to r, it's 1 over the ln of something, 1 over the inside times the derivative of the inside with respect to r, so in this case I'll just be 3. And then I'll do the same thing for the rest of them. So it'll be 6 over 3r plus 6s plus 9, and 9 over 3r plus 6s and t. And just to get our stuff all in order, I also want to evaluate this at that given point, 1, 1, 1. So that'll just give me 3, 6, and 9, which is, what is it, 27? Is it? No. 18? 18. Well, that simplifies a little bit, right? 1, 6, 30. All right, so the last step is a dot product. And then, so you got, I'll take the 1/7 out here, and then 2 6, 6 thirds, oops. 6 over 3 is 2, I think, and then 3 halves. And then whatever that simplifies to. Suppose I can just type that in and then get an answer. It'll still be correct, right? Okay. What happened? Oh, that's good. All right, number 9 was the next one. Hey, this kind of looks like the quiz, huh? Hey, maybe I got the quiz questions from here. All right, we have a temperature, and then we want to find the rate of change from one point to another point. So that one point to another point is actually giving us our direction. So our direction vector here, we'll call it V, is equal to 5 minus 5, 6. And that's the head minus the tail. This is where you came from. 2 minus 1, 2. So this is going to be 3 minus 4 and 4. Is that right? And then so I want to make this into a unit vector. And so 4 and 4 is 16. 16 plus 16 is 32, plus 9, 41. So 1 over square root of 41 times that vector is going to be my unit vector. I want my gradient. And so 100 is a constant, and then e to this thing, the derivative of that is e to that thing times the derivative of the inside. So With respect to x first, I'll have negative 2x popping out. Actually, all these will have 100, e to the negative x squared minus 3y squared minus 7z squared. So the only difference is that I'll have the extra factors of the derivative of the powers. So the first one is 100 e to the negative x squared minus 3y squared minus 7z squared times the derivative of the power, which is negative 2x. Second one will have 100 e to the negative x squared minus 3y squared minus 7z squared times the derivative of the power with respect to y, which is negative 6y. And then the same thing. Okay. Now you're at the point 2, negative 1, 2. So you want to put in 2, negative 1, 2. And then I have 100 e to the 4 plus 3 is 7. 7 plus 28 is 35, right? And then minus 4, positive 6, and negative 28. So that's my gradient evaluated at that point. So I just dot them. I just multiply this out. So the directional derivative is going to be your t, the gradient of t dotted with u, which is really just the dot product of these things. Oh, 100 e to the 35 in the denominator, square root of 41, and then the dot product, I get negative 12 minus 24 minus 2, 3, 102. Is that right? 4 times 28. So I could leave it like that, I suppose, and then punch it in the calculator. 112? Close. And this is degrees Celsius per meter. It's the change in temperature with respect to the distance that this is flying. Distance can be going in any direction, but that's what it's looking at. Which direction does the temperature increase the fastest? From this point, you can just put in the gradient of t that you found over here, or since you just want the direction, right? You can ignore the coefficients out in front, and you can even take out another 2 out of this, I think, right? So it would be, instead of the gradient of t, you can say it's a gradient of t scaled. And then you can say the direction is going to be negative 2, positive 3, negative 14. And that should work also. So any scalar multiple of the gradient gives you the direction. I mean, you could put this whole thing if you want. Doesn't matter, but that'll be a little bit quicker. Find the maximum rate of increase. You want to actually take, not scaled, but you actually want to take your gradient and then find the magnitude of that. So the magnitude of that is really, let's see, I'm going to take that 2 out. and just find the magnitude of the leftover vector, minus 2, 3, negative 14. So since the magnitude of a scalar times a vector is equal to the absolute value of the scalar times the magnitude of the vector, we'll just take the scalar out and then just take the magnitude of the vector. So whatever this is, squared, square root. So what's 14 squared? 196? 196. What?
209.
Square root 209. So I think that should work as an answer, unless they tell you they don't. I don't see anything where they say round off to the nearest whatever. All right, so let's put some of those numbers in and see if it actually will work the way they bring it up like this. So first, this thing, let's put this crazy expression over here. Do we need to put a vector there? No, that's multiplication. Which direction does it go? I think we took this gradient and then we scaled it by 2 or by 1/2. Do we need a vector for this? So that's a minus 2. So it has to stay negative 2, positive 3, and negative. The signs are still important because this is the increase. If you go the other way, that's the fastest decrease. So 3 and then negative 14. And then the last one was some weird, crazy thing that we decided to simplify, strangely simplify. 200 times e to the negative 35 times the square root of 209. All right, let's see how it goes. It's all half simplified. But it should still work, right? Because that's what they're asking for, is they're asking for these expressions as expressions. And what happens when you type this stuff in is that it looks at it, it parses it, and then puts it into Mathematica, and then calculates it and see if it's equal to the correct answer when they simplify it. So that's why you can fiddle around with weird answers like this. All right. Any more? Should we go on to another section? Should we look at the review? What? 14.7. Oh, this one, you know. That's from the video, so sorry, you have to watch the video. I would normally do it, but I spent a lot of time on that video, so you better use it. Damn it. So look through it and see if you can. Was there a 14.8 one? Any of them? So stuff to look forward to. But I'm hoping the rest, aside from that weird plane problem, I'm hoping the rest of 14.7 is okay, because it's what's important. So 14.8 is a 4 problems. Maybe that's why you guys had so much before. Let's do all of them. What? Well, let's do as much as we can. I should turn off the video so the people that left won't be able to see this. Huh? A lot of people left. I guess I shouldn't care. Picture on contour map are f and g. So f is the function that you're trying to maximize or minimize, and then g is your constraint. Usually that's how it's set up. Estimate the maximum and minimum values for f subject to the constraint. So your blue lines are f, and then there's one contour for g, and that has a contour height of 8. That's the level curve for that. So what we want to do is we want to look for places where it looks like it's kissing. I kind of see these two as obvious, but there's one more right around here. This one is not quite kissing over here, right? Because one graph looks like this, and then the other graph looks like this. So they're not. Well, I wouldn't consider that as tangent to each other. So I only see those 4 possibilities. And so now that you know those 4 possibilities, what do? Well, you want to, let's say this point is 0, comma something, x naught, y naught. So what you need to do is you need to put x naught, y naught into the function. And when you put it into the function, what do you think you're going to get? You're going to get. You get what? No? It's at that level curve. So it's at that level, whatever level it is, right? And so if we look at the level curve that touches at that point, that level curve has a value of 60. So if this touches exactly, I would put 60. If this is a little bit off, I would, give or take, and then we'll talk about which give or take when we take a look at this other one. So this is a little right on the dot thing. So I would say this particular x naught, y naught is going to give us an f value of 60. And it looks like there's another one over here. This one will be, I need to look at it closer. So let's call this x1, y1. I should just call it P, not P. Let's just call it P. So f of P, f of P1, which has x1, y1 components in it, is going to be 30. So we have possible maxes and mins already. Let's see. Let's take a look at this, because this is another candidate for an extrema. And for this one, let's call this P2. F of P2 is going to be, okay, so now it's not exactly touching 50. So I want to go either 51 or 49. What do you think it'll be? It'll be 51. So this is 50. Now this is on the side where the level curve increases up to 60. If this was on the other side, then it would be going down to 40, but this is increasing up to 50. So I would go, I say plus and minus some number, so I would go plus because the next level going in that direction goes up, so 51. And then similarly over here, if you just designate this to be P3. So it looks like we found the maximum and the minimum, and that's probably all we need to do here. 60 and 30. All right, the next one, let's see if we have. Two, three, or four. We need to just pick one. Two. Sorry, I heard two first. So Lagrange multipliers. With the given constraint. So we're going to consider this as our g function, and so we need the gradient of f, which is negative 2x, comma 2y, and then we need the gradient of g, which is 1/2 x, and then 2x, or 2y. And then we throw that lambda in front of one of them and then add them or set them equal to each other, and we get our three equations. So negative 2x is equal to lambda 1/2 x. Positive 2y is equal to lambda 2y. And then our third equation is the constraint. Now we have this thing again where I'm really tempted to divide by x, but I can only do that as long as x does not equal to 0. So I'll make a case where x is not equal to 0, but then I have to remember to check the case where x does equal to 0 as well. So when x doesn't equal to 0, my equation would be lambda is equal to, the x's would go away, the 1/2 would be a 2, lambda is equal to negative 4. And I'll put that into the second equation, 2y is equal to negative 4, 2y. Is this going to do anything for me? Y is equal to 0. So 0 and 0 isn't going to work. Oh no, I said x was not equal to 0. So if x wasn't equal to 0, I'll use my third equation to see if I can solve for x. So x, this is 16 times 64, and then take the square root of that. It's 8, but don't forget that the positive and negative options for this. So I have 2 points out of this. We got 8, 0 and negative 8, 0. So I'll remember to check that into my original function. So our other option, if x was equal to 0, then the first equation wouldn't give us anything. The second equation wouldn't give us anything either. But if we put it into the third equation, we can get y. So y is equal to plus or minus 4. So we have 0, 4, and 0, negative 4. So remember, these points are not your answers. What you need to do is you need to plug it into your f function. So we could do that pretty quickly, yeah? So y squared minus x squared. So we got zeros in for y. So our f here is going to be negative 64. Whether we put a plus or minus, we'll get the same answer. Our f here is going to be positive 16. Again, whether we put a plus or minus is going to be squared. So it looks like those are our max and min values. Let's just check. Okay. So the tricky part is solving for those equations. If you are banging your head trying to solve for equations, you're really having a hard time, go to Wolfram Alpha, type in solve, and then write down those equations and the variables you're trying to solve for. And that might alleviate some pressure. All right, tomorrow we're starting integrals, chapter 15.